Okay, hello everyone, welcome back. Since last we spoke, I have learned some technology. In particular, I've learned how to put myself in the corner of the screen over here. So this is great fun for me and hopefully for you as well. Okay, so let's get started. If you recall, last time we had built quite a lot of technology ourselves. In particular, we developed this LSZ formula, which related matrix elements, so products of in-states and out-states, with time-ordered correlation functions of field operators. Today we're going to use that to finally actually calculate something. In particular, I want to calculate a 2 to 2 scattering amplitude. So I want to find the amplitude for 2 to 2 scattering in this lambda phi to the fourth theory. So to be more precise, what I mean is I'm going to imagine that there are two particles coming in, K1 and K2, and these particles now can scatter off of each other, something can happen, and then two particles will come out, K1 prime and K2 prime. These are, of course, the momenta of the incoming and outgoing particles. And I want to calculate the probability for this to happen. In other words, I want to calculate the following matrix element. I want to calculate the inner product of the initial and the final state, which in this notation now I would write as K1 prime, K2 prime as the out state, inner producted with K1 and K2 as the in state. So I'm going to calculate this inner product. Okay, so we know how to do this. We have in fact a very lengthy formula for exactly this. That formula is the LSZ formula, which in this context looks like this. The LSZ formula is that the inner product of f and I is the integral. So I'm just reproducing a formula from earlier. So what I do is I take the Fourier transform of all of the variables, x1 dot 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 for x1 prime e to the plus ik1 prime dot into x1 prime, and then I multiply this with the time-ordered correlation function, which is t phi of x1 dot 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 dot. Actually, there's not that many. Let me just write out what they all are. Phi of x1 prime, phi of x2, phi of x2 prime. And finally, there are also some kinematical factors. For every field, there is a kinematical factor, which is the momentum going in multiplied by k squared minus m squared. So I have k1 prime squared blah, 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 all the way up to the last one. So of course, there's one of these for every field operator here. I'm just not writing them all out. And this thing is the LSZ formula. It relates, as I said earlier, the inner product of f and I with this matrix element. Okay, with this time-ordered correlation function. Okay, so what we need to do now is we need to calculate this 4-point function. And for notational reasons, I'm going to denote this 4-point function in the vacuum as G4 as a function of all the xi. This xi denotes x1, x2 prime, x1 prime, x2 prime. Okay, and I'm going to call it G4. So I need to calculate this thing G4. Now, happily, of course, we know how to do that. So let me also introduce a bit more notation. I'm going to abbreviate, just for notational reasons, I'm going to abbreviate the functional derivative j as a function of xi. I'm going to denote that by delta I. And there's also a factor of minus I here, which is useful. So I'm going to denote the functional derivative with respect to j of xi by delta I. This is just notation. In that case, we can conclude that the 4-point function g4 of xi is given by 1 over z of j times the derivative 1, derivative 2, derivative 1 prime, derivative 2 prime of z of j, all evaluated at j equals to 0. And again, we derived this in previous lectures. Okay, so we take 4 functional derivatives of z of j, and we get the 4-point function of the phi field. Okay, So now we need to calculate z of j, and again, we've derived a diagrammatic formalism for doing this. In particular, in this diagrammatic formalism, what we need to do is find all the terms in z of j with 4 j's in it. And then each of these functional derivatives will ultimately associate one of the j's in there with one of the external legs, with one of the external points. Okay. So I'm going to do this now order by order in lambda, as usual. So let me start with the calculation at order lambda to the 0. Okay. So first, order lambda to the 0. And what do we find? Well, to first order in lambda, there are 3 diagrams that contribute, and we've worked them out already. They look like this. If I have 1, 1 prime, and here I have 2, 2 prime, there's one diagram that looks like this, one diagram that looks like this, and one diagram that looks like this. Okay, and if you think back, we did this in the very first lecture. We worked out that these are the things that contribute at order lambda to the 0, in other words, in the free theory. Okay, so I want to examine these terms. By the Feynman rules that we discussed, we know what these terms are. I want to examine the Fourier transform of this. So let me study this Fourier transform. What does this look like? Well, what I do is I take each of the points and I do an integral of the following form. d4x1 e to the minus ik1 dot x1 all the way up to the last one, d4x1 prime e to the plus ik1 prime x1 prime. And what is the diagram itself? Well, the diagram itself, as you can see, is a Feynman propagator from x1 to x1 prime, multiplying another Feynman propagator from x2 to x2 prime. Okay, because we have these 2 legs, each connected by one propagator. So I now want to understand this Fourier transform as a function of k1 and k1 prime. Okay. So the first thing to note is, by translational invariance, this propagator doesn't care about x1 and x1 prime independently. It only cares about their difference. So I can write this like this. x1 minus x1 prime times df of x2 minus x2 prime. So the next thing to note is that because this integral only cares about the differences between these points, the sum x1 plus x1 prime doesn't actually enter anywhere in the propagators. It only enters in the exponent in all these Fourier transforms. So I can rearrange the Fourier transform to make this more explicit. In particular, let me rearrange the exponent like this. So in the exponent, there is a term that looks like k1 prime x1 prime minus k1 x1. So I can rearrange this in the following way. k1 minus k1 prime x1 plus x1 prime plus 1/2 k1 plus k1 prime x1 minus x1 prime. Okay. All right. And now, if you recall, I'm integrating over all of the spatial coordinates, but the integral over x1 plus x1 prime is very easy to do because it doesn't enter into the integrand at all. It only enters in the exponent of this e to the I k dot x. So in other words, I can just do this integral, and what happens is I get, from doing the integral over x1 plus x1 prime, I get a delta function in k1 minus k1 prime. But what does that mean? if you think about it, this means that the incoming momentum k1 is equal to the outgoing momentum k1 prime. So that actually implies that k1 is equal to k1 prime, which means that actually there is no scattering happening here. In other words, the one particle is coming in and it's just becoming the one prime particle without anything going on. And okay, we have done a lot of math to show this, but it's actually kind of obvious from this picture, right? You can see right here that the one particle is going in and becoming the one prime, the two particles going in and becoming the two prime, and there's no scattering going on. All right. So very similar considerations apply to all of the other disconnected diagrams. And in particular, what is happening here is that all the disconnected diagrams do not contribute to scattering. They don't cause scattering. So what that means is we should think only about the connected diagrams. So that's what we're going to think about from now on. We're going to focus on the connected diagrams. Now, if you recall, we actually know how to do that in a very nice way. We introduced last time this object IW of j, which was the generating functional of connected diagrams, not disconnected ones. So what all this means is we should use this when calculating scattering amplitudes. In the LSZ formula, we should think only about the connected 4-point function, which I will denote like this with a subscript c, where c here is for connected. And this is equal to the following functional derivative, the 2 prime of IW of j at j equal to 0. Okay. And indeed, IW of j is trivial to lowest order in lambda. It only becomes non-trivial at first order. And so there's no scattering at order lambda to the 0, which makes perfect sense. So now we go to the next order in lambda. Now we go to order lambda to the 1. And now we finally have something interesting happening. At order lambda to the 1, there is one diagram which is contributing, which looks like this. Here I have x1, x2, x1 prime, and x2 prime. This diagram contributes and is non-zero. Okay? And you can see what its contribution is to the 4-point function. What we get is that this diagram gives us something which looks like this. G4 of xi connected is equal to minus I lambda, where that comes from this vertex, minus I lambda, times the integral d4y. This point you can think of as y, which is being integrated everywhere. And then there's a bunch of propagators. There's a propagator from x1 to y. There's a propagator from x2 to y. There's a propagator from x1 prime to y, and finally there's a propagator from x2 prime to y. Okay? But these are these 4 propagators here that I've just drawn. Okay. Now, to evaluate this, it turns out to be extremely useful to go to momentum space. So let's do that. Okay. So next I want to go to momentum space. So I want to Fourier transform everything here. And let me say at the outset, what's going to follow is a little bit excruciating, and I'm doing this because I want to do it in full and gory detail. After we do it once in gory detail, we will not be quite so careful about it. You can understand how the bits and pieces fit together, but for now I'm going to do this in full excruciating detail, so I apologize for that. Okay, so to go to momentum space, what we do is we Fourier transform everything. So in particular, I use the representation of the propagator, which we all know and love. In momentum space, any propagator takes the following form. It looks like this, 2 pi to the 4th, e to the plus or minus ip x minus y, I over p squared minus m squared. In the exponent, we can actually pick what we like. in this exponent. It doesn't really matter for the final answer in this case, but it is good to pick that exponent to line up with the power coming in the LSZ formula. Okay. So what that means is it is good to pick the positive exponent for the in states and the negative one for the out states. That makes, I'll just make sure I got that right. Yes, that's right. That makes all of the momenta line up nicely with the momenta coming into the LSZ formula. So if I do that, if I insert this representation here, into each of these propagators, then what I find is that the amplitude becomes G4 of x I connected is, here we go. So first of all, the integral d4y survives. I now have a bunch of new integrals over each of the momenta. So, and there's a factor of 2 pi to the 4th for each of them. Next, I have a bunch of things in the exponent. So they are ip1 x1 minus y plus ip2 x2 minus y minus ip1 prime x1 prime minus y minus ip2 prime x2 prime minus y. And finally, I have the product of all of the propagators, so this goes all the way from p1 squared all the way up to p2 prime squared minus m squared, and there are 4 of these propagators. Okay. So just to be clear what's going on here, I have Fourier transformed each of these propagators, and now you should imagine that there's a momentum flowing in each of these legs. In particular, in the notation that I used earlier, I have P1 and P2. The momentum is going in, and the momentum is going in because of these plus signs that are here. And then I also have going out P1 prime and P2 prime. And here the momentum is going out because of these minus signs here. All right. Okay, so now let's take a step back and stare at this expression. Let's look at the y integral for a second. Okay. So where does y enter? Y enters only in this exponent. It enters, for example, here, 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 and here, and nowhere else. And what that means is that the integral over y gives us an overall delta function which looks like 2 pi to the 4th delta p1 plus p1, p1 plus p2 minus p1 prime minus p2 prime. Okay. So what does this mean? This means that the momentum that goes into this vertex is equal to the momentum that comes out of this vertex. Okay? And that follows from this integral over this y. Now, okay. But now, when we insert this expression into the LSZ formula, there will be a bunch of integrals over x's. If you don't recall that, I encourage you to pause and go back and look at the LSZ formula to remind yourself what the integrals over x's are doing. And each of those integrals over x's is going to tie the internal momentum, which I've called P, to the external momenta, which I called K. Okay. So let me just write that down in words. The integral over x's in LSC ties the p's to the k's, in other words, sets them equal to each other. And furthermore, the LSZ formula also had a bunch of factors. It had a bunch of p squared minus m, or k squared minus m squareds in the numerator. Each of those k squareds minus m squareds is going to cancel the I over p squared minus m squareds in this expression right here. Okay. And so what happens then is that each of the p's becomes the same as one of the k's, and each of the p squared minus m squareds cancels these guys. And so at the very end, what we find for the amplitude, so not for the correlation function, but for the amplitude, is that k1 prime, k2 prime out inner producted with k1, k2 in is just minus 2 pi to the fourth. Let me put this all on the next line. Is just equal to minus 2 pi to the fourth times delta of 4 k1 prime plus k2 prime minus k1 minus k2. And finally, there's a crucial factor of I lambda. Okay, so this is the final answer for the amplitude. And one thing I should say is that there is a z in the LSZ formula. And I set that equal to 1. We'll discuss that later. It turns out at order lambda, it does not get changed. There's a chance to correct it at order lambda squared, but we'll discuss that in the next lecture. Okay, so that was a lot of work. All right, so it's possible the bits and pieces of how this fit together weren't immediately clear. So I encourage you to pause the video, scroll back upwards, and just make sure that it's clear how this sort of painful combination of kinematic factors all conspire to give this answer in the matrix element. The really important thing here, of course, is really this I lambda. All of this stuff here is just kinematic. This delta function just tells you that momentum is conserved in the process. This 2 pi to the 4 doesn't mean that much. What's really happening is that it's telling you that there is a chance for these particles to scatter, and the probability is given by lambda. It's really kind of incredible. If you actually went and built an accelerator and smashed together mesons of this kind, the amplitude really would go like this. Like, it really does actually work. Okay. So that was, again, quite excruciating. And from now on, I'm going to be much more schematic about it. So for future reference, I'm going to define an important thing. Let me define the so-called invariant matrix element. And that's the following. Basically what I'm doing is I'm imagining that I have a product of in states and out states, an inner product, sorry, of in states and out states. And this inner product takes the form 2 pi to the 4th delta 4 sum over the incoming momentum minus the sum over the outgoing momentum times Im of k. The invariant matrix element is called I curly m, and it's just this bit here at the end. Okay? So what I'm doing is I'm basically stripping off all of these sort of tedious kinematic factors, and I'm focusing on the interesting important bit. I'm calling that Im of k. It's the important bit with all the kinematic factors stripped off, all these delta functions and so on. So from this calculation, it's clear that our expression for the matrix element, oh, excuse me, I left out a minus sign here. There's a minus sign there. Our expression for the matrix element in this previous calculation is simply Im equals to minus I lambda. That is what we get from this matrix element. Okay. Okay. So from here, it should also be clear how the momentum space Feynman rules work. I'm going to write them down for you, but I'm going to put them in a separate video just so it's easier for you to come back to them. But basically, what we've done right now is see how the momentum space Feynman rules work. Okay, I'm going to put that in the next video.